Hi, everybody, and thanks for joining us for this Docker live meetup, broadcasting from Kansas City. So today we will have two talks, one short introduction about Docker, and then I will dive into something called Live Without SSH, which describes how to use Docker and containers without running SSH within the containers themselves. All right, so I will share my screen so you can see the slides and the demo that we're going to have. Right. So first, we'll start with an intro to Docker. So this is like the regular Docker 101 material. So for some of you, this might be familiar, but I hope that there will be some interesting demos that might be interesting or surprising to you. So for a short introduction about myself, I'm Jérôme Petazzoni. I work for Docker as a senior engineer, and before Docker was Docker, it was .cloud, and there I was operating and scaling our platform as a service product, which was built on top of EC2, LXC, and so therefore containers, and that's how I logically was able to transition seamlessly with Docker. I contributed a few interesting features into Docker. The most interesting one being the privilege mode, which allows us to run Docker within Docker, or also VMs within Docker, so that you can run Docker within a VM within Docker, and then get extremely confused. So this is what I want to talk in this presentation. First, what's Docker, what it matters, then a short explanation about containers, what they are technically, then present Docker ecosystem, then how to get started with Docker, and then we will switch to Live Without SSH. So what's Docker, why it matters? So the goal of Docker is to deploy everything. So anything that we can deploy on a Linux machine, then we should be able to deploy it inside of Docker. Web application, API backends, databases, big data stores, message queues, anything. And the goal is to be able to deploy everywhere or almost everywhere, because for now, Docker aims at deploying only on Linux servers, whether it's a virtual machine on your laptop or desktop computer, on a virtual machine in a cloud, public or private, or a physical machine. It also aims at being able to deploy to any distribution, the only requirement being that you have to have a recent kernel. We demand at least kernel 3.8. If you have an older kernel, Docker might or might not work, but please don't even try, because we are tired of getting reports of people telling us, hey, I tried Docker and it seemed that it worked fine, and suddenly it crashed. It seems that obviously this is not stable. And in fact, after investigating, it turns out that they were running kernel 3.2, which is not supported at all. Docker officially runs only on Intel 64-bit machines, but we know that there are people out there who got it working on Raspberry Pis and other non-Intel architectures. It's just that officially we don't support that yet. And recently, Microsoft announced that they would add Docker support to Windows. That doesn't mean that you will be able to run Linux applications on Windows. That doesn't mean that you will be able to run Windows applications on Linux machines. It means that you will be able to run Linux on Linux, Windows on Windows, but you will be able to run both workloads in containers. And you will be able to control those containers, to deploy them, to run them, to scale them, to orchestrate them using the same API, the same tools, the same management platforms. So today, all the things that we are building with Docker on Linux will be available tomorrow for Docker on Windows. And for the ops persons managing those containers, there will be no difference when they do I want to start this bunch of containers on this machine. For them, it won't make a difference whether it's a bunch of Linux applications running on Linux servers or Windows applications running on Windows machines. Then one of the goals of Docker is to achieve reliable and consistent deployment. So since those words are often pretty loaded, this is what we mean. We want to avoid that syndrome where the dev team on the Friday afternoon throws a bunch of code at the ops team and tell them, okay, guys, good weekend. And then the ops team tries to get that to work, but it doesn't because on the developer's laptop, they had all those libraries and they were running Fedora. And so they had everything kind of set up for that code, but all those dependencies were not expressed in the code. So when the ops team, which by the way is not running Fedora, but CentOS is trying to get that running on the servers, it just doesn't work. It's missing dependencies, missing libraries, and that ends up with big problems between your dev and ops team, and nobody wants that. So when we say that we want to deploy reliably and consistently, it means that if I get something to work on my laptop and I ship that to the ops team, I want it to work just as well. Even if we don't use the same distros, even if we don't use the same versions of the distros, even if I have some packages installed and they don't have it, we want to have something that is self-contained. If you have already used virtual machines, you might think, well, we could do this with VM images. I could just put my code and everything in a VM image and then give a VMDK or something like that to my ops team, except that this is not really convenient. I don't want to give a 5 gigabytes VM image file to my ops team each time I need to fix a one-line CSS change in my code. So instead, we want something that will be lightweight, and also something that will be lightweight not only in disk usage, but in memory and CPU usage. Some people did benchmarks to compare speed of containers versus speed of physical machines of VMs. And they found out that when you use containers, there is no difference in speed. For instance, this is a benchmark comparing throughput and latency in an InfiniBand cluster on physical machines and in containers, and as you can see, there is absolutely no difference. This is a benchmark showing that it is faster to run a bunch on containers rather than a bunch of virtual machines, and then they also use less memory, and those VMs and containers end up running exactly the same thing. This is a benchmark of memory speed, and once again we can see that containers and physical machines have exactly the same performance, while VMs are a little bit slower. So don't get me wrong, the goal is not to say throw away all your VMs now and replace them with containers and save a bunch of money by stopping paying licenses to VMware. The goal is to be able to use both. The question is not VMs or containers. The question is VMs and containers. What I wanted to show here is that it's okay to add containers on top of your VMs because that's not adding any overhead. So you keep all the management features and the isolation features of your VMs, but you're adding the deployment convenience of containers. So some people sometimes wonder, why is it that there is no overhead at all with containers? The reason is that a container doesn't add any emulation or abstraction layer. A container is just a bunch of processes that run directly on the host kernel, and they just have some tags and labels indicating, hey, this process is actually isolated in its own container. And when that process is trying to access the outside world or just to look at what are the other processes running on the machine, then the kernel will show it only its own little private world. So containers are not here to make a strong isolation, but just to give a separated vision to those processes. So what is Docker exactly? Docker is made of two parts, the Docker engine and the Docker hub. So the Docker engine runs containers. But what exactly is a container? So from a distance, a container is a lightweight virtual machine. I can SSH into it, even though we will see in the next part that we can also completely get rid of this requirement. If I SSH into my container, I will see my own processes, my own network interface, private IP address. I can do almost everything I could do on a VM. I can set up firewalls, I can install packages, I can run services. It's great. So it really looks like a VM. But at the same time, as I said before, a container is just a set of processes. So I don't have to run init and syslog and cron and SSH and all those things. I can also just start directly the process I need. I want to run MySQL, I start MySQL, and that's it. So I have a quick demo to show that in action. So I have Docker. I interact with Docker with the CLI, and I typically do Docker run, and then I want, let's say, an Ubuntu container. So I do Docker run -ti Ubuntu bash. And here I'm in a brand new Ubuntu container. I have a bunch of files here. I can say, okay, hello world. Now I have an hello world here. Now let's say I exit this container and start a new one. Well, my hello world file is gone because I started a new container from a brand new image. The other one is still around. I can still get back to it and see my hello world file if I want, but I just wanted to show that each container is independent. They have their own packages, and just to prove that I'm not fooling you, you can see that on my machine I have much more packages than inside this container. I don't like Ubuntu, no problem. I have a Debian container instead. Well, not Debian, yeah. And there I have even less packages because our Debian images are extremely lightweight. You don't like Debian-based distros, that's fine. We can have Fedora instead. Obviously, no DPKG here, but RPM. And I don't know exactly how to list the packages with RPM, so I won't show you how many packages there are here. I will just show you that I can even have CentOS if I want, and so that's great. Okay, so that's what the first interaction with the Docker engine looks like. I can start containers, I can do things with them, I can install packages, and that's it. So how does it work? Technically, containers are based on two sets of kernel features, namespaces and control groups. The namespaces are the things that will make each container believe that it's alone. When I start my Ubuntu container here and I check the processes, I only see the processes of the container, which are different from all the processes in my machine. If I check the IP address of my container, it has this IP address. And if I start another container, then it will have another IP address. And those IP addresses are obviously different from the ones on my host. So that's the PID namespace, the net namespace. I have also a few other namespaces to provide isolation with my containers. Then there are control groups, which are here to limit and meter and account the amount of memory and CPU and I/O done by containers. So I can prevent one single container from eating up all the resources on my machine. Okay, so at this point, we could think those containers are like lightweight and cheap virtual machines. That's great. We run tons of virtual machines, so let's run containers instead and we will just save a bunch of money. Nope. It took us a while to understand that containers were not just a virtual machine and that we could do much more interesting things with them. Let's look at this. When something becomes suddenly much cheaper, or faster, or there are two things that happen. First, well, there is a bunch of things that we used to do and that we will continue to do, except that we will do them for a lower price or faster, or we will do them more often. And then there are things that were completely impractical because it was way too expensive, or it was kind of crazy to do it, and suddenly it becomes possible and we do it and it changes a lot of things. Let me take an extremely bold example. Let's talk about like the GPS system. When we just had planes, we could build planes going higher and higher, and we could have had planes with radio emitters and use that as a kind of GPS system, except it would have been like super expensive because that would have meant having hundreds of planes constantly in the air. Each time one plane lands, you have another one take off. So it's not really realistic. You can do it, sure, technically that's fine, but it's not realistic. Now, if you can make planes that go very, very, very high in orbit, and then you call that a space rocket, then you can use that to launch satellites that will remain up there kind of forever, and then you can have the GPS system, and then it's realistic to have that. So we're not going to throw stuff in space with Docker, but we're going to make testing cheaper and easier. Let's look at this example. Let's say I have a project that has 100 unit tests. I hope your project have tons of unit tests as well, because unit tests are great. And let's say that each of those tests needs to interact with a SQL database. So each test needs to have a perfectly clean database. You have multiple strategies. One strategy is to have one database for all your tests and for everybody to use. The problem is that if one of your tests leaves the database in the wrong state, all the tests after that will fail. Or if you're doing your test and someone else is doing tests and using the same database at the same time, that will fail just as well. So you need to make sure that you clean up each time. And that cleanup can be slow and expensive. Like maybe it means that you have to reload a 1 gigabyte dump from the database. So another solution would be, well, each time I need to run my tests, I'm going to spin up 100 databases in VMs, and each of my tests will run against one of those VMs. That's extremely expensive, and you generally won't have the money to do that, because what we want to do is that each time you commit a single change of code in your repo, we want to run those tests and make that happen. So if I must spin up 100 VMs each time I push some code to my repo, that's not going to fly. So our solution is to run 100 databases in containers, because I remember when I did this docker run -ti ubuntu bash, it started kind of instantly. So we want to do that with databases. And I have a little demo showing how to do that. So I have prepared an image that has a Django database in it. And so I will start run test here. And this has started a container. If I run this, so docker ps, here I have my test DB, which is running. And so here I can see a bunch of tables. So this is my database. And let's say that one of my tests is to destroy that table here, the drop table of group. And I had to put cascade because there are dependencies, and I just want to say, let's destroy all those things. Okay, and so I've destroyed that table. It's not here anymore. Now I exit, and now I run again, and it just takes a couple of seconds, and the thing is back here. And I have not reloaded a SQL dump or anything like that. I've just started a new copy of a base image, and that base image contains this database. So I can do whatever I want with that database, and that database could be multiple gigabytes. That wouldn't change anything. It would just work just as fast. So containers have made testing way easier and faster, but not only testing. I'm talking about testing because the people working on all those automated testing systems, CI/CD that you hook up with your GitHub or Bitbucket repos, those folks have been among the first ones to run Docker anyway, even when we were saying, don't run Docker in production because it will set fire to your house and abduct your dog and very bad things will happen to you. They would run Docker in production anyway, because for them, it changed everything. It made some things that were either impossible or extremely inconvenient. Well, those things suddenly became easy. So let's see the Docker ecosystem. We have the engine, the hub, the community, the company. So the engine, well, that's this little thing I just demoed. So it's an open source engine to commoditize Linux containers. Commoditizing meaning making them extremely easy to use. for everybody, not just for Unix black belt gurus that have been using containers for 10 years. It's using copy on write, so that even if I create a container based on a 1 GB database image, it will be instant. It's written in Go. And one important thing is that all that Docker does is actually exposed through REST API. When I did Docker PS, Docker run, Docker something, Docker whatever, it actually creates an API request and sends that over a local socket to the local Docker daemon. But if I want, I can start a bunch of Docker hosts in a cloud somewhere. And from my local machine, I just have to tell to Docker, hey, instead of talking to the local machine, talk to that remote server over there, and it will work exactly the same way. Docker also has a build system that we will demo in just a minute that lets me define recipes for my images to automate building them. And then I can share them with registries in the Docker Hub. A little bit of fun phases on open source. Everything happening in in Docker, in the source code, is public. So you can go to GitHub, to the Docker repo, and see everything, including the embarrassing bugs, including the roadmap, including the things that will be in the next Docker release, because before being in the next Docker release, they are part of a public pull request that is reviewed by Docker maintainers. Then the Docker Hub is another component of the Docker ecosystem. The best comparison we can make is a parallel with Git and GitHub and Docker and the Docker Hub. Git is open source and free. You can do all kinds of awesome things with Git without giving 1 cent to anybody. But GitHub is extremely convenient and nice. It likes a free hosting service for your code. It has nice side-by-side GIFs. It has the pull request workflow. That's what we want to try to do with the Docker Hub. Docker is also free and open source, and you can use it as much as you want without paying anything to anyone. There is no light edition and enterprise edition. There is only one edition of Docker, but there is a Docker Hub. The Docker Hub lets you host your container images. It lets you set up an automated build system so that each time you push something to GitHub or Bitbucket, it will notify the Docker Hub. The Docker Hub will get your code, it will build it, and it will upload the result to the Docker Hub. And the Docker Hub will also have more and more features to add to it. And then there is the community, and some of those numbers here are a little bit out of date, but there is one that I would like to emphasize: the fact that we have more than 600 contributors to the Docker code base, which means that there are 600 people out there that change something inside of Docker, even if it's a small, like one-line fix. And then the company, well, that slide is also slightly out of date because it says that we are 60, but I think we passed the 70 bar recently. But basically, that means that less than 10% of the people working on Docker open source are actually hired by Docker Inc., which means that the project is really driven and steered by the community. That's extremely important because we all know about those open source projects that are great and awesome, but where most of the contributions were done by a few people paid by some company, and suddenly that company gets acquired by a big evil company, and then the open source project dies or forks, or well, things become different. So you can be pretty confident that this is not likely to happen to Docker because most of the development is driven by the community anyway. So how do we get started with Docker? The one-time setup, so how do you install Docker basically, is to either use boot to Docker or just install Docker directly on your machine if you run Linux. If you don't run Linux, the thing is that, as I said earlier, Docker currently runs Linux containers on Linux machines. So you need a Linux machine. But to make this easy to you, we have something called boot to Docker. It's a tiny VM image that will that is also the kind of the smallest Docker install that you can ever find. So it can be useful when you are evaluating, testing Docker, but also later when you decide to use it for real. Because the boot to Docker is not like the trial version, lightweight something of Docker. It's what the Docker developers and maintainers and everybody using Docker out there is using when they are not on Linux. Now, when you want to deploy to your servers, well, we have packages for virtually all the distros out there. If you don't like packages, you can also just download the Docker binary and run it, because that's one of the upsides of Go, that you can compile a program to a single binary that embeds all its dependencies. It's a almost static binary, and that just works. If you want to run on public cloud, we have either ready-to-run images or really easy provisioning instructions to run on most big providers out there. There are even distros that have been created and built specifically to run containers, like CoreOS and Project Atomic. So I talked about the fact that Docker has a format to define the build of a container. That's the Docker file. This is a sample Docker file where, and I will show that in action just here. So the idea is that the Docker file starts with a from line explaining the base image that you want to use for your container, and then it has a bunch of run lines indicating a number of steps that must be executed to build your container. And then it has a little bit of metadata indicating what should run inside the container and if it's exposing any kind of network service. This is actually a bigger deal than it looks, because the old format for containers was kind of to ship a tarball containing a root file system. Say, okay, this is the tarball. Now you can just run that with Elixir or chroot. But you don't know exactly what you're supposed to run. So here we define exactly what should be started in the container. In that case, that's just a static web server with Nginx. And expose is a kind of hint to tell, hey, by the way, this container is going to have something running on port 80. So when we expose that container to the public world, that's what we want to show. So now we will build that. So I will do docker build -t-web dot, and so it will execute dot steps. So now it's running apt-get update. And once it's done executing that, it will take a snapshot of the resulting container, and it will reuse that snapshot to execute the next step. The whole point is that if later I want to change my container, I will be able to change my Docker file, or for instance, in that case, what I will do is that I will change a little message in the hello world in my container. And when Docker rebuilds the container, it will be able to restart from the latest snapshot. You see, it took a snapshot of the result of apt-get update. Now it's installing Nginx. And when it's done with that, it will also take a snapshot of the result. So let's give it a few extra seconds to do its job. And then once this container is built, I will run it. And so previously I've been doing docker run -ti, but now I'll be doing something slightly different. I will do docker run -d, that's mean detached or demonized. So run that container in the background, -p, which means publish all the ports. So all the ports that have been declared, have been exposed here, will be made available. And I run like this. Now I do docker ps. It's telling me that my port 80 was exposed to port 49156. Okay, so I'm going to a browser and I'm going there, and yeah, fine. I see, hi, I'm in a container. That's great. Now, what happens if I say, well, I want something different here? Say, hello world, I am in a container. Slightly different message. And now I do docker build -t web version 2 dot. So it's almost instant, because Docker knows that it already has apt-get update somewhere. It already has the result of apt-get update and apt-get install somewhere. We have snapshots of those, so it can use cache and use the container image which was in the cache. However, that command is new here. so it has to execute it like for real. But this command is fast and lightweight. Earlier, the thing that took forever was the apt get updated and apt get installed, and we can skip that now. So the build was really fast, and I can run that container again. So -d -p webv2 docker ps, and it's on the next port. Okay, so now I'm going to that port, and I demo effect. What's going on? 49157. 49157. Interesting. Okay, did not start properly. That's interesting. So I will just show another Docker command, docker inspect. So docker inspect will tell us a bunch of information about a given container. And here I just want to make a little of live debugging to show you, okay, what do we do when something doesn't go as expected? So here I'm looking for the IP address of that container, and I'm checking, yeah, my container seems to be alive. Maybe I can, yeah, so apparently the container is up and running, but the kind of the outside plumbing didn't come up correctly. That might be something going on with my local machine. I will just give it another chance. I will try to start just another copy of that container. So now I have the first one, and then the new version here and here. So 49158 now, 158. Yeah, and that works. So maybe I had something on my machine blocking that port. So an interesting thing here is that if I want to roll back, if I decide, well, after all, I prefer hi rather than hello world, I can just go back to the older version here. I can switch between versions easily. If instead of being a simple hello world, this were like an actual production app, I would have a load balancer, and I would be able to switch between versions using my load balancer. And my old image is still around, so I can start, because I called it differently. It's web and webv2, so I can restart my old web image if I want to. This is a slightly more complicated Docker file if I want to run CouchDB. This is another Docker file if I want to run a Python app. So Docker files can be more complicated than that. They can have more steps if you want to. Those are just like, for example, purposes. If I want to run multiple containers now, because usually an app is made of many things, so then I will use something called Fig. Fig lets me describe a stack of containers inside a FigYAML file. So this is an example where I have a Mesos master, a Mesos slave, and then the Vault framework all running in a Fig stack. And I will show a quick demo of that to show what Fig looks like. So I have my FigYAML here with my 3 containers, and then I just do Fig up, and it's creating my container and running them and aggregating the output of all of them. And now if I go to localhost 8080, right? This is what I just started, and this is a front end that lets me start containers using an API. This is a web front end, but it actually makes requests to an API. So I can start like a Redis container, and it will spin a little bit. And now it's running. If I check the output of my container, I will see the Redis output all right. So what you typically want to have is you want to have for each of your components a Docker file, and then for your whole application a FigYAML file. And when someone joins the team, you tell them you install Docker, for instance, with put to Docker, then you clone the project repo, and then you Fig up. And within a minute, you have the whole application and all its dependencies, all its services up and running on your local machine. People often ask us if we have integration with configuration management systems. For the purpose of this presentation, I will just say that yes, we do. Next thing. So that's like the midpoint summary. So with Docker, we could put our software in containers, run them anywhere. We could write Docker files to automate the build of those containers and use Fig to start multiple containers. So there is a Q&A app on Hangouts. So you can use it if you have some questions. I will check if some people have entered some questions already, and then I will check. I will go to the second part of today's presentation. So there might be a weird effect when I switch back to the Hangouts interface. Yes. So QA. Okay, so nobody asked questions, which might be because I hadn't told to people before that we might be using that. So if you have questions during the second part of the presentation, you should see the Q&A application. It should be the left side of the Hangout windows. If you have joined through the Hangout interface, you can use that to ask questions. All right, so let's switch to the second part now, which will be without SSH. Okay. So it's and let's go. So life without SSH, that's a more advanced topic. So it all started a while ago when Fusion released this. They made a pretty big blog post about your Docker image might be broken and you're not even aware of it. It's terrible. We have to help you to build the right Docker file for your application. Our solution is the Fusion-based image. And it was kind of a little bit going in a different direction from what we were advocating, because our idea was we want you to run just what you need inside your container, so that that container can be extremely lightweight. You want to run MySQL, you just start MySQL in your container. You want to run Apache, you just run Apache in your container. We have often said we would like you to run one process per container. It's not exactly one process, because it's okay for your Apache or MySQL or whatever service to start sub processes, and we don't want you to have like one container per sub process. It's just the idea of one service per container. And this base image was adding cron, SSH, and syslog, and it in some ways, yeah, it's fine, because it helped a lot of people to transition from a kind of VM workflow to a container workflow. So that's great. But and generally, people told us, but yeah, we love that image because it's awesome. It's incredible. I can SSH into my containers and I can do stuff. And I was thinking, no, you don't really need this SSH to do things in your containers. We can do all those things without SSH. And it started as a kind of thought experiment, really. And it ended up being way more than that. So let's see how we manage to do all the stuff we usually do inside of containers with SSH, but without SSH. Let's look at logs. Usually you would SSH into your container, go to /var/log, and then run all the tools that you learned and love to inspect logs. The newer approach is to use a data container. So a data container is a container that exists, is here, but doesn't run anything. It's just here to contain data, hence the word data container. And the thing is that in that data container, we have a volume, which is a special directory. Here you can see -v/var/log. That means /var/log is a volume. And that volume will be shared across other containers. So how does that work? I've created here a data container named logs, where /var/log is a volume. Fine. Now I'm going to start my app, which is my application container, and I will tell it volumes from logs. So reuse the same volumes. It means that in the my app container, /var/log will be the volume shared with that data container. And now I can start another container, a log inspection container that will also use -- volumes from. And basically that container will have exactly the same /var/log. And so I will be able to tail, grep, arc, and whatever my log files. If I want to use some special like this fancy grep written in Perl inside, to check my logs, well, instead of installing that on my production server, inside my production application container, I can put that in a separate container and run it here. So now I can have a kind of toolbox container with all my favorite tools, even if those are extremely exotic tools, and I can check my logs with them without having to install extra stuff on my production containers. If I want to ship my logs, like to send them to an ELK, Elasticsearch, Logstash, Kibana cluster, if I want to ship them to a syslog server or an external service like Loggly or Splunk or Papertrail or whatever, no problem. Instead of doing that inside my application container, I will do that in a separate container that will share that /var/log directory. So now, if I want to switch from one logging system to the other, instead of changing my application container, I just send this special sidekick container. And I don't have to change, rebuild, or even restart my application container to do that. So that's great. Let's see now how we do backups if we don't want to use SSH access, because the traditional approach is that I just SSH into my server and I install all the packages I need, like rsync, and then I have a backup script and I run that backup script. And if I want to run a backup every day at 5 a.m. in the morning, then I just put that in a cron tab. With containers, this is what we can do. We can have a separate container to do our backups. We will use data containers just like before, but that time not for the log files, but for the data files. And then when we will start our database, for instance, we will use that data container so that the precious data files are on the data container. And then I can start the backup container that will have all my tools, and I can tell that container to reuse the volumes, the same volumes. So now this special backup container has access to the varlib MySQL directory of my MySQL database, and it can safely back up this and send that wherever I want. If I want to do daily backups, that's where things get really interesting. I could run cron in one container and keep that container running forever, and every day at 5 in the morning that container could cron would wake up and kick the backup job, but that would leave me with one container running forever even while it's not necessary. So for each of my databases I would have an extra backup container running all the time. Not so great. Another option is, well, since I have that container that can do like a one-shot backup, I could have the cron tab entry on the Docker host. So on my Docker host, I will put something that does a Docker run, make my backup. And so that way I won't have extra containers lying around. Or if I have a bunch of databases that I need to back up, then I could have just one special cron container, so one versus like one per database, and that container would have access to the Docker API. So I would empower that container so that it can do Docker run, backup this database, Docker run, backup this other database. And so that container would start other containers. The end result is that now I have separated, on the one hand, the fact that I'm running something on a daily basis, on the other hand, the action of actually backing up the database. Let's see how we do network debugging. So, when this web server is misbehaving and you don't really understand what's going on and you want to dump the network traffic and sniff packets, and so you use something like TCP-dump, ngrep, nload, Wireshark. So traditionally, you SSH into the server and you install those tools and you run them. With containers, this time we'll use something other than data containers. We will use network namespaces. This means that we will make a special network debugging image with the tools that we want to use, and we will run a container based on that image with a new option, --net container colon and the ID of the other container. This container will share the network stack of your application container. It will have the same network interfaces, the same IP addresses, and if I do TCP dump on ngrep or whatever in that container, I will see the traffic of the other container. Okay, now sometimes we want to SSH into the machine and just change one line of configuration and restart the service. How do we do that with containers? Well, I could tell you, yeah, in that case you make a new image, but it could get a little bit boring when you just want to make one small change to configuration and restart, another change and restart again. So it's all about fast development lifecycle and agility. So if you have to do something long and boring instead of something which was fast, it means that we failed. So how do we do that? Well, the traditional approach is like SSH, edit config file, restart. How do we do that with containers? Don't be fooled by the fact that the slide is longer. It's actually just as simple. The idea is that you just put that configuration directory on a data container, and then you can start your application container using that data container. So now /etc/tomcat in my example can be shared across multiple containers, and then you start a special container to edit that configuration. And so in that container, you will edit your configuration file, and then you just restart the application container. This solves also another problem, which is when your ops team tells you, nope, you can't have Emacs or Vim or this or that on the production servers because we don't want to install that crap on our servers. So you have to use some like Nano or really basic VI editor or something like that. So in that case, you solve the problem by having a container that has your favorite editor and everybody is happy. Your ops team because you're not polluting the application containers, and you because you can have your favorite editor and environment. What if you really, really, really need a shell? Well, in that case, we have something. If you're using something before Docker 1.3, there is nsenter. And just look for nsenter if you're still using Docker pre 1.3. But I don't want to spend too much time on that because now on Docker 1.3 and onwards, we have Docker exec. You do Docker exec, the ID of your container, and you get a shell in the container, and that's it. Just exactly as if you had made SSH into that container, even if that container doesn't run SSH, of course. To show you another interesting one, so this very complicated command line is about gathering metrics for your containers. So the idea here is that instead of installing Cacti or Munin or collectd or something like that inside your containers, and even instead of installing it outside of your containers, you can install it in a separate container. And that very complicated command line here will give visibility to that container over the other containers in the machines. In other words, that container will be able to gather metrics for all the other containers on the system. That's another interesting example. And so after writing all those things, after writing that blog post explaining, okay, this is how you can do things without SSH, I came to realize something, is that we are achieving composition. Because on the traditional system, we typically install everything like side by side, the base system, the libraries, your application, and then logging, backups, metrics, security, remote access, firewalling. And if we are using config management, then we will have a manifest that looks like that when we include a number of sections and everything gets brought together. But this can have a few problems. For instance, if some of those components have different requirements. Here, for instance, what if the logging and metrics subsystems both are using Java but require different Java versions, or they kind of work if you use this Java version, but really one of them would work better with an older version or whatever. Or if you want to run some security auditing software, but that has been only certified on RHEL 6.4, but really you want to run Debian on Ubuntu. So with containers, what we do is that we still, of course, have the Linux-based system, but then we have Docker, and then each thing is in a separate container, and those containers share just enough to be able to work correctly. The application container and the logging container will share the log directory. The application container and backups container will share the data directory. Application and metrics, well, as we saw, there is some kind of magic complicated command line so that the metrics container can see everything it needs to see, and so on and so forth. So with starting with like life without SSH, we ended up actually building container composition, which was kind of one of the issues we had with Docker files in the beginning, which is that when you build a Docker file, you build it on top of a previous Docker file, which means that if you want to compose multiple things, it kind of doesn't work. There is no like multiple inheritance, but that's how you achieve it. You run multiple separate containers and you let them share just enough context so that each of them can do its job. Thank you. I will see if some people got the Q&A app working on Google Hangout, and nope. So, well, we are almost out of time anyway. Well, thanks a lot for attending. We might want to find an easier way for Q&A next time. You can always reach us on our usual channels. We #Docker and #DockerDev IRC channels on Freenode, where the community is pretty active. You can also use the Docker user and Docker Dev Google groups, which are mailing lists, which are also extremely active. So that's like the most basic ways to get some help. And I can also encourage you to subscribe to the Docker online meetup group, where we try to do those kinds of meetups on a monthly basis, to give some content and insights about what is going on in the community. So someone is telling me to wait for the questions, so I will stick around maybe a minute or two. Okay, so questions might be coming. Meanwhile, I will try to put up on the screen some useful links, maybe. Yeah, so I'm showing up some other, so a recap on the IRC channels, a few contact email addresses, and if you have questions, once again, you can use the Q&A app, which should show up on the left side of the screen. And okay, so one question is, what's the preference CoreOS? So I suppose that the question is about what are like the pros and cons of CoreOS? What are the strong sides of CoreOS? Should we use it? I will kind of twist the question a little bit differently. People often ask, what's the best distro for Docker? Should we use CoreOS because it seems to be like dedicated to Docker? So is that like the best container distro ever? And the answer is just continue to use whatever you were running. If your ops team is used to Ubuntu, continue to use Ubuntu because we have packages for that anyway. Just make sure that they use like the latest LTS, like 1404, because it will have a recent kernel which will be stable and everything for Docker. If they use CentOS, then go for like at least CentOS 6.5. Preferably 7.0 if they can, and so on and so forth. If you want to really embrace a 100% container workflow, and if you're ready to run everything inside of containers, so if when I talked about this life without SSH thing, you are like, okay, this is great. I want to put all those things in containers, and I even want to get rid of all the processes on my servers. I want all those things to be in containers. Then you might be ready for something like CoreOS, because the key idea is that you're not installing anything anymore on the distro itself. Everything has to be in containers, because basically, to simplify the picture a little bit, when you do an upgrade, you get rid of the entire distro, you just keep the containers and you put another distro instead. So whatever you would have installed in the distro is lost. So it's a new concept. It also comes with a lot of really interesting features, like, well, there is etcd built on top of it, so it gives you a configuration database to store lots of things about your configuration for your applications. It comes with Fleet, which lets you distribute jobs across your servers. But it's a really new way of doing things. So go there only if you're ready for a significant kind of change. Then another question is, what's the best way? Okay, so I can select this question and then, okay, done. What's the easier way with AWS? How to deploy and use Docker on AWS? So there was a big announcement at reInvent in Vegas a few weeks ago about the Elastic Container Service. This does not, this hasn't shipped anymore. So don't expect to be able to use ECS right now because it's not there. Another option on AWS is to use Elastic Beanstalk, but you should not really be using that because it's extremely limited. It will only let you run one container per EC2 instance. So all the nice things I described here will not be possible. So I don't recommend anyone using Elastic Beanstalk on AWS. This won't be like a great Docker experience. The approach that we like to use right now is just to use your favorite distro on AWS, whether it's Ubuntu or Debian or Fedora or the Amazon Linux. Install Docker on that. We have an install script. If you go like to get.docker.com, it's a script that you can run and that installs Docker on your distro, which means that you can use that as a Cloud Init payload to transform any Cloud Init compatible image on Amazon into a Docker instance. This means that you can take all the Ubuntu, Fedora, Debian, etc. Images on Amazon and turn them into Docker instances extremely easily with that Cloud Init script. And so that's today the easiest way to get started with Docker on AWS. The next question is, when VMs are better fit than containers. So My favorite example is when you run a huge compute cluster and you have like 100,000 nodes, and you do some benchmarks and you realize that within VMs you have like a 5% performance overhead, which is pretty typical for VMs. That translates to 5,000 nodes. That's a lot. It means that in your data center, you have rows and rows of racks filled with machines that are here just because of the virtualization tax. So if you have lots of machines and you have that virtualization overhead, then it might make sense for you to try to replace VMs with containers to get rid of that overhead. Because of course, being able to save like thousands of machines, that's a big deal. However, if you just have a few hundreds of nodes, then that 5% overhead translates to just a few machines. So it's a trade-off. It's a decision that you have to make. Do I want to invest time and therefore money to be able to replace VMs with containers just to save a few machines? Maybe not. So it's really a matter of scale. If you are a huge organization with tons of resources, it could make sense. Otherwise, you're in the general scenario where you will want to use VMs plus containers. The next question is, would you say that Docker is a layer between the operating system and application and daemons, which Docker is exposing with APIs to these daemons? So I would be tempted to say that Docker is not really a layer. It's more like kind of a mechanism, a platform to start those containers, and the goal of Docker is, on the one hand, to package and wrap the applications or daemons and services and expose them to other services. So that part is definitely accurate. Docker will help you to make that kind of plumbing between services and applications. It's just the term layer that tickles me a little bit, because we usually don't really see Docker as a layer. It's kind of out of the way, in the sense that it will start containers, it will manage them, but it's kind of out of the execution path. You can kind of make the Docker daemon disappear and everything continues to run. All right, and I think that was the last question. Thanks a lot, everyone. And once again, if you enjoyed that format, I would recommend you to check the Docker online meetup group, because we do those broadcasts on a regular basis. Thanks, and have a nice day or evening, depending on the time zone where you're currently on. Bye-bye.